So, welcome to office hours. What can I do for you?
Well, I think I resolved the issue I had.
Yeah, you sent me a message saying you weren't clear about the instructions on 4 and 5, but you feel more comfortable with them now?
Yeah, when I realized that when I sent the email, somehow I didn't think a counterexample would involve numbers for some reason. So like in problem 4, I was trying to think of a way to like algebraically express a prime number, and my brain just like exploded.
Yeah, my brain would explode too. No. So yeah, you just want particular numbers to make that negation true.
Okay, I got that done, and then same thing with 5. I got that done. I found two numbers that worked, and then I proved it, I think.
Right, because it is false.
Yeah. So I think I'm pretty much good then. I just wanted to tell you so that you wouldn't be worried.
Did you get my message that I replied? I think it was either early this morning or late last
Um,
night. I did respond in the messaging app
oh, you did?
or email, one or the other. I thought I did.
Oh, you did. Okay. I guess I didn't see it.
It's okay. It's probably been a busy day,
Yeah, definitely.
right? Things start getting really busy this time of year.
hmm
Okay. Nick, do you have a question? Nick might have stepped away.
Sorry, I didn't realize my mic was muted. A little bit in the same boat. I was on question three. I was a little bit confused by it, but I think I got it. I just was wanted to know if you could walk through it to make sure I'm on the right path.
Okay, so on number three, you're actually trying to prove that statement. And we've got three numbers. A is even, B is odd, and C is even, right?
Yep.
And you want to prove that AB minus BC is even.
Mm-hmm.
So I'm assuming that you assumed that A is even, B is odd, and C is
C is
even.
even. Yep.
And you wish to show AB minus BC is even.
Yes.
Perfect. And then you just apply the definition of even and odd.
A equals 2q where q is an integer, b equals 2r plus 1 where r is an integer, and then c equals 2s where s is an integer, right?
Right, right. So, yeah, you assume A is even, B is odd, and C is even, right? And just to be thorough, we wish to show AB minus BC is even. Right. So you said by the definition of even and odd, or by the definitions of even and odd, what were your equations?
A equals 2q where q is an integer,
A
b
equals
equals
2Q, where Q is an integer. I like it. Keep going.
B equals 2r plus 1, where r is an integer, and
2R plus 1, where R is an integer. I like it.
C equals 2s, where s is an integer.
Nice. C equals 2S, where S is an integer. Exactly right. And then if we want to expound on our wish, we wish to show AB minus BC is like equal to 2 times M, right?
Yep.
Where M is an integer. And then you just went through the uh, the algebra.
Yes.
And there's some, I mean, it gets a little involved, but it's not too bad.
Yeah. Um, that part, that part was what got me, but I did figure out what it was.
Cool. We're just gonna plug in 2Q for A, 2R plus 1 for B, minus, we got to be careful with the minus sign, right?
Yep.
2R plus 1 times 2S. So what do we got, like 4QR plus 2Q. Here we got to be careful. Minus 4RS minus 2S.
I put 4SR. Does that make a difference?
Nope,
Okay.
nope, multiplication doesn't care.
All right. Just making sure.
Multiplication does not care, what order we put the factors in. So 4SR is the same thing as 4RS, or negative 4SR is the same thing as negative 4RS.
Okay. And I understand the
Right, and then you pull out the 2. And you get this big expression, and that's your M.
okay.
Cool.
Yeah, I got that. All right, thank you.
Hey, Charles.
How you doing?
We're good. How are you?
I'm good. I'm good.
So we're just looking at this special homework number 5, I'm assuming.
Uh,
But we can talk about
uh,
other stuff too.
I was gonna ask because in the special homework you wanted us to do the good step 1, but the only questions I seen that we could really apply it to was, let me see,
If it wasn't
the
already,
word because I what'd you say?
yeah, if it's already written as an if then, like I think on number 1, you have to use it.
Yeah, number 1 and number 4, I believe.
Yeah, if you want to first write the original statement as an if then, for number 4, that's fine. And then you would use the fact that the negation of an if P then Q is that there exist numbers that are prime and distinct, and the sum is not prime. You want to look at number 4? Shall we look at number 4? Or are you okay with that?
Yeah, we could look at some number 4.
Okay, so number 4 says, yeah, I think I started you off on the if then, but here we go. The sum of any, and I threw a new thing in there, this idea of distinct. That means they're different from each other. Primes is always prime. So if we write the statement, as an if then, I think I used P and Q. So let's finish it. If P and Q are primes, and this idea of distinct just means they're different. In other words, we can just say, and P is not equal to Q. That's the same thing as saying they're distinct. What's the then part?
Uh, then P arrow Q.
No.
I'm sorry. I know what the arrow stands for.
Oh, yeah. Okay, so here we're using P and Q not to represent statements, but to represent actual prime numbers. We want to
Okay.
talk about the sum of P and Q, because these are numbers, not statements, okay?
Okay. The sum
So,
of ages.
yeah, so how do we write the sum of P and Q? Using, P and Q and some symbols.
P and Q upon and P plus Q.
Yeah. And P plus Q is always prime. So that's really good, because what that lets us see is it lets us see, what we call, the big P, I'll call it A, curly A. If A, then B. This is an if A, then B. Okay, because we're using P and Q for the numbers. We'll use A and B for the statements. Does that make sense?
Okay.
Yeah, I mean, sometimes we wind up reusing variables because there's only 26 letters in the alphabet, and there's a couple of those we can't really use. So we wind up, changing things around a little bit. But the negation thing to remember is that an if then is always universally quantified. This is about all numbers P and Q. So in the negation, we would say there exist P and Q such that, here we go. The negation is A happened and B did not follow, okay? Such that, so A happened, so P and Q are primes and they're different. P is not equal to Q. That's curly A. And this conclusion, which we're calling B, didn't happen. So P plus Q is not prime. That's not B. Does that make sense?
Okay.
So that's what we're actually going to be proving, is that there are some numbers, P and Q, where the P and the Q are actually primes and they're not the same primes, and their sum is not prime. So you just got to find primes, P and Q, that are different from each other, and then you got to look at P plus Q and make
Yeah,
sure that is composite. Have you had a chance to do some scrap work?
yeah.
Have you found a
Uh,
few that'll work?
I came up with the values that made the negation true, values 3 and 5.
That's exactly what I was hoping you'd come up with. You keep it small, keep it simple. These are definitely primes. And they're definitely not equal. So you would say that. And then P plus Q is 8, right? And so you just have to show how you can factor 8 into two factors that are both bigger than 1. What were the factors that you used?
Oh, 2 and 4.
Yeah, exactly. So, 1 is less than 2 and 1 is less than 4. And these are both clearly integers. So you have to say all that.
Okay.
So you want to write it up nice. You can look at all those proofs and counterexamples that we worked on day 10. So you can see day 10 notes, and it'll help you write it up properly.
That's kind of similar
So this
to
is
what I
just,
had.
yeah, this is just scrap work. It's not really the counterexample. It has to be written up as a good, nice counterexample. Do you know what I'm saying?
Mhm.
You would start, counterexample. Part C. You're going to actually, write the word counterexample, and then you're going to present, let P equal 3 and Q equal 5. You're going to verify, we actually have to verify
Yeah, verify each.
that this is a prime by talking about, hey, its only divisors are 1 and 3. Verify that Q is, 5 is a prime because its only divisors are 1 and 5, right?
Yeah.
I mean, you have to say that part. You have to actually go through and verify that these actually are. I mean, we know they're primes, but why are they primes? Because we know they don't have any proper factors. Oops, lost my video. Just like when we're verifying that 8 is not prime, we're actually factoring it and talking about those factors being bigger than 1. See what I mean? So when you get ready to write it up, look at the proofs and counterexamples that we wrote up in the day 10 notes so that you make sure that you address all these bits and pieces properly. And you're going to, use sentences and everything. It's not going to look like scrap work. It's going to be presented like a nice proof. Well, actually a nice counterexample.
Okay.
It's a proof with the negation, of course.
All right, I'm starting to get the hang of it.
What? You're starting to get the hang of it? Good.
I mean, yeah, yeah.
Like all that stuff we learned about if-then statements and their negations, and I mean, that stuff really, is important now.
Well, that's all I really wanted to go over for. Other than that, that's it. Possible grade making up. Is there like extra credit we could do at the end of the?
I'm going to pause the recording for a moment until you have a question.
Number two.
So, still looking at homework 5. I'll share my screen. We can look at number 2 together.
Okay.
Okay. So number 2 says, consider this statement. Why don't you read the statement?
Exists a prime number p such that p minus one minus one is composite.
That's right. There exists a prime number p such that 2 raised to the p minus 1 is composite. Exactly. And it says this is a true statement, and it's an existential statement, right?
Mm-hmm.
So we can prove this by example. So you're going to show some scrap work. You're going to hunt around for a prime p that makes this expression composite. Do you remember the definition of composite?
Let me just look at my notes book.
Sure.
There we go. An integer n that equals, was it greater and equal to 2 is composite if there exist integers a and b such that.
That n equals a times b, and 1 is less than a and 1 is less than b. In other words, we can find a way to factor a composite number into a product of 2, what we call non-trivial factors, 2 factors that are both bigger than 1.
Okay. So look at this. Look at
Like
this.
12 is composite, right? Because 12 equals
Yeah.
3 times 4 or 2 times 6. There's a couple of ways to break it down to show it's composite.
All right, look at some examples of prime until you find one that makes the predicate to be as composite. Show the scrap work.
So you're going to show your scrap work and just poke around, and try some different primes. Of course, the advice is keep it simple, keep it small. Like, don't try like a huge prime number. Like, try some small ones and see if you can make it work, because it'll be easier.
So basically, we're just looking for a number that would be bigger than 1, pretty much.
Are you talking about p?
Yeah, sorry, p.
We're looking for a prime. P has to be prime. Let's take a look at what this thing says. There exists a prime number p. So, yeah, p is going to have to be bigger than 1 for sure. But it also has to be a prime. Like, you can't use p equals 6 because 6 isn't prime.
Right.
And then, we want to pick a prime p such that this expression 2 raised to the quantity p minus 1, whole thing minus 1, is composite. In other words, we want to be able to factor this expression 2 raised to the p minus 1, whole thing minus 1. to show it's composite. Let's do some scrap work.
Let's just I'm just throw one out. Let's say 7.
All right, so if we try P equals 7, that's definitely going to be a prime. So now we're going to look at 2 to the P minus 1, whole thing minus 1. So it's 2 raised to the 7 minus 1, whole thing minus 1, right?
Mm-hmm.
So what is this? 2 to the 6th
Mm-hmm.
minus 1. But what is 2 to the 6th?
That would be 64.
That's right. So we're looking at 63. Is 63 composite?
Yes.
All right, how can you factor it to show it's composite? You got to find an A and a B.
Oh wait, no, it wouldn't be composite.
Well,
Actually, no,
I
wait,
guess you
no.
didn't learn your, I guess you didn't learn your times 9 or your times 7 times tables when you were in 3rd grade.
That was really good. I just totally forgot about it.
I know. Who was? My best friend's mom had this multiplication table, I swear, pasted on the bathroom wall next to the toilet. And she would practice them, and my best friend would practice the multiplication tables and get stars.
Oh wait, it's 7. Yeah, it's 9.
7 times what?
9, 7, and 9.
Great. So that's the first part of showing it's composite, but then you got to talk about 7 and 9. You have to verify. 7 is an integer. Just say it, 9 is an integer. And you got to verify that both of these are bigger than 1, or that 1 is less than both of these. You just say it. That's all you do. You just got to just state this. That's good enough. But you do have to say this part, because this is part 2 of the definition of composite, and this is part 3. So you'll show this work, and then you'll talk about 7 and 9, why they work out to show that 63 is composite.
And this would actually be composite because it is an integer. And it is bigger than 1.
Yeah, both of these 2 factors have to be bigger than 1.
Yep.
You found your example to prove it. Good job.
Okay. Yeah, that makes it. Write a proof of the statement. Is that what we just did? Write the proof of the statement?
Yeah, you're actually proving an existential statement. We prove an existential statement by example. See, it's a there exists statement.
Okay.
That's the nice thing about existential statements. We can prove them with an example. We just have to prove the objects exist.
Okay, so
We have to verify, that everything works out. But yeah, as opposed to proving a universal statement, which we cannot prove using an example. Universal statements, if-then statements, have to be proven using variables and definitions in algebra.
yeah. Verify the predictable holds wherever choice of P be thorough and address all parts of the working. Okay. So then what the scrap work is A, and then the B would be just the verify.
Yeah,
Correct?
when you write the proof, there are always 2 things to verify. We got to verify that the object that you chose 7, really lives in the correct domain. So you're going to have to verify this is prime. In your proof, when you say, hey, consider P equals 7, then you're going to, say, hey, 7 is prime because, well, why is 7 prime?
Because it's bigger than 1.
No.
Oh, wait, sorry.
I mean, that's part of it, but a number that's
It's
bigger than 1 could be prime or composite.
yeah, it's odd also. Sorry.
It's okay, but 9 is odd and 9's not prime. You need to review the definition of prime. It's only positive divisors are 1 and 7 itself. That's what makes it prime.
Okay.
It doesn't have what we call proper divisors. You see, 63 has what we call proper divisors, divisors that aren't 63 or 1. You know, both of these divisors, 7 and 9, are bigger than 1. See, that's the difference between prime and composite. So you
Okay.
have to verify that 7 really is prime, and then you have to verify that this expression really is composite by treating, all the parts of the definition of composite. This is part 1 of the definition of composite. Is first you factor whatever it is in that you're trying to prove is composite into A times B. Okay, so that's part 1. But this is part 2 of the definition, where you verify that these two factors are both integers. And then part 3 of the definition of composite is when you verify that both of these are bigger than 1.
Ugh.
I know, there's a whole bunch of parts to the definition of composite. It's kind of a bear.
But no, I totally get it.
All right, cool.
I think that might be it for me.
Okay,
Thank you so much.
thanks for playing.
Have a good rest of your night.
Thanks. I'm going to pause this now.